Hi everyone, my name is Michael Amir, and I will be presenting a walk fast uniform dispersion of a crash-prone swarm. In swarm robotics, a huge number of simple and autonomous robots must work together in order to achieve complex goals. In this walk, we study a well-known coverage problem in swarm robotics called the uniform dispersion problem. In the uniform dispersion problem, which is a theoretical algorithmic problem, a huge swarm of robots enters a discrete environment over time from one or more source locations. The goal of the swarm is to completely cover this discrete environment as soon as possible, such that every location contains at least one robot. An important constraint is that a given location in the environment can only hold a limited number of robots. So in order to finish the mission quickly, the robots must coordinate their movements such that they do not obstruct each other. This kind of problem is easy to solve with a centralized planner, but becomes more interesting when we try to consider the local and autonomous nature of the robots. As such, most works on this subject are focused on achieving uniform dispersion despite severe constraints on hardware and communication. In this work, we assume that the robots activate in asynchronous time with no global clock, that they operate on very low memory, and that they can only communicate with robots in their immediate vicinity. To quickly explain the slides to the right, this is a simulation of our paper's algorithm. The source from which robots come out of is the box that I've just circled, and the arrows themselves are the robots. The direction of the arrow represents the kind of message that the robots send, and the color red indicates that there are two active robots in the same location. So the idea of this flavor of swarm robotics is that it trades off more sophisticated and expensive robots for a vast number of simple, autonomous, cheaper robots. Despite using simpler robots, it has been claimed that swarms are highly fault tolerant, as redundancy and sheer numbers can enable the swarm to go on with its mission, even if many robots malfunction. However, a sort of counter-argument to this is that as the size of the robotic fleet grows, so too does the opportunity for error. Specifically, three different complications that arise in multi-robot systems are further exacerbated in the swarm setting, and these are robotic crashes, where a robot simply crashes and stops walking, traffic obstruction, where robots block each other off from progressing, and lack of coordination due to each robot being autonomous and not synchronized with the others. So a main goal of our paper was to check how sensitive our swarm is to such issues. How much is performance impacted by their presence? Can many robots even be worth it if they come at the cost of more crashes and complications? So what we do in our paper is present an algorithm that completes the uniform dispersion mission and formally prove results about its sensitivity to error. In the spirit of swarms, the algorithm is simple and purely local, meaning the robot's behavior is affected only by local communication. The algorithm works by having two layers of robots. Robots start in the active layer and search the a priori unknown environment for an unexplored location where they can join the settled layer. When a robot joins the settled layer, they point to or mark the settled robot in their last location. New active robots then follow these marks to efficiently find new locations in a kind of branching graph algorithm. In the paper, we prove, roughly speaking, that crashes, asynchronicity, and movement obstruction do not have a disproportionate impact on the swarm's performance. If C is roughly the fraction of robots that crashed, and N is the size of the environment, the swarm completes its mission almost surely in asymptotic N over 1 minus C time, which is comparable to the time you would expect it to take in a fully coordinated, synchronized scenario where robots never interfere with each other. We did not find in the literature a way of modeling asynchronous multi-robot systems of this kind in such a way that allows us to talk about and bound their performance time. Instead, we derived our model from a well-known model in statistics and physics used to model such things as vehicular traffic called the totally asymmetric simple exclusion process, and used tools from it in the analysis. Our model and the tools from statistics that we used in its analysis might be of interest to people who wish to formally study the performance of asynchronous swarms of a kind similar to ours. Thank you very much and have a wonderful day.